In section 4, we're going to be talking about polar coordinates. And polar coordinates are useful for when we're going to be graphing what's sort of on a unit circle, but we can assume that we can have any angle and we can actually have any radius. So we're graphing using an angle and some distance r or radius. So a polar coordinate is when we travel from the origin going a certain distance which we are going to call r and a certain angle. Which we're going to call theta. And we get at a point. So the way we represent a polar coordinate is by r theta. It's that distance r and that angle theta. So let's go ahead and plot some polar coordinates. So when we plot polar coordinates, we always travel theta first. We always apply the degree first, and then we apply the radius, that distance r. So our first example, 4 pi over 3, we want to travel pi over 3 first. So I know these aren't labeled, but this would be pi over 6, this is pi over 4, and this is pi over 3. So we're going to travel from the origin a distance of pi over 3, and then we want that radius to be 4. So that's going to give us a point right there. It's on that pi over 3, and we've gone out 4 from the origin. Okay. Next, we want to graph the point -2, negative pi over 4. So the first thing we're going to do is travel that negative pi over 4, which is going to be down into the 4th quadrant. And then if I actually travel out to 2, this is actually a radius of +2. If I want a radius of -2, I then go in the opposite direction out 2. So over here would be the -2, and then I'm going to go to -2 along the same degree. So this would be my point -2, negative pi over 4. Next, we want to graph the point 3, 0. So we start with our theta, which is going to be 0, which is just the origin. I'm not moving anywhere, and then I want to go out a distance of 3. So it'd actually be on that r axis just at 3. Lastly, we want to plot the point -2, 7 pi over 4. So if we find 7 pi over 4 on our unit circle, it's going to be down here in the 4th quadrant. And then again, similar to that second example we did, if I plot a point with a radius of 2, this is a +2, 7 pi over 4, and if I want that radius to that r to be a negative distance, I go the opposite direction to -2, and we get -2, 7 pi over 4. So this point -2, 7 pi over 4 is actually the same as that example we did above, -2, negative pi over 4. They have the same radius, and their thetas are actually going to be in the exact same place. So when they are plotted, they represent the same polar coordinate. And that actually is what we're going to cover next, how to identify when polar coordinates represent the same point. So there are a couple different ways you can figure out polar coordinates that define the same point. So one way is if you want to keep the same distance, which is r. So you want r to stay the same, but you want a different theta that represents the same point. So there's a couple different ways you can do this. You can either find a coterminal angle to theta, in which case it would be in the same place, or you can take your angle theta and subtract 2 pi from it. So if you were to travel the negative distance that lands you in the same place as your theta, that would give you the same polar coordinate. The other way we can look at it is if we want to go a negative distance. So if we're going to change r to be its opposite sign, we have to figure out what theta would be. And there's actually only two ways you can do this. Theta either gets you add pi to it, or you can subtract pi to it. And that will give you the same polar coordinate. So this is doing a negative r, and the way you find the same point. Let's go ahead and take a look at a couple examples. So we have the polar coordinate 1 pi over 6, and we want to find some other coordinates which represent the same point when graphed. So in our first example, we want r to be greater than 0, and we want theta between 2 pi and 4 pi. So what that means is we're going to keep r the same. It's going to be 1. So r is going to stay 1. But we want to find those values theta, but this time we want them in between 2 pi and 4 pi. So one way is to find a coterminal angle. So if I take pi over 6 and I add 2 pi to it, that will give me a coterminal angle. 2 pi is the same thing as 12 pi over 6. So I can get 13 pi over 6. So one angle would be 1/13 pi over 6. The other way is if we keep theta the same and we subtract 2 pi from it. So if I do pi over 6 minus 2 pi, we're going to get a negative 11 pi over 6. But this is not between 2 pi and 4 pi, it's actually between 0 and 2 pi. So what we're going to do with this angle is subtract 2 pi from it, and we'll get a coterminal angle within our interval. So when I do that, 2 pi is still a 12 pi over 6. We end up with negative 23 pi over 6. So another point would be 1, negative 23 pi over 6. Both of these polar coordinates represent 1 pi over 6. So now we want to take a look for if a radius is less than 0, but we're still between 0 and 2 pi. So this time, r is going to equal negative 1. So the way we find polar coordinates represent the same point is we take our theta, pi over 6, and we add pi to it, and we subtract pi from it. So we're going to do pi over 6 plus pi, which is the same thing as 6 pi over 6. So we're going to get 7 pi over 6. So we have the point negative 1, 7 pi over 6. And if we take pi over 6 and we subtract pi, we end up with negative 5 pi over 6. So we have another point, negative 1, negative 5 pi over 6. So another useful thing is being able to convert from polar coordinates back to those rectangular coordinates. So that's given a point xy. You have an x value and a y value. It's what we're more used to when we graph a point. So when we convert from polar coordinates to rectangular coordinates, it's helpful to know that x is found by taking your r and multiplying it by cosine theta, and y is found by multiplying your r by sine theta. And these are going to be very useful to us. So we want to find the rectangular coordinates given a point in polar form. So we have the point 4 pi over 6. So what we're going to do is r is 4, theta is pi over 6. So to find our x value, we're going to do 4 times cosine of pi over 6. So it is going to be useful for your unit circle here so you know how to evaluate. So we end up with 4 times cosine of pi over 6 is radical 3 over 2. When I multiply these, I can go ahead and do the division first, and 4 divided by 2 is 2. So we get x equals 2 radical 3. We're going to do this the same way with y, except we're going to do 4 times sine of pi over 6. And using the unit circle, sine of pi over 6 is 1/2, and 4 times 1/2 is 2. So we get y equals 2. Which means our rectangular coordinate is 2 radical 3, 2. So if you were to compare a polar graph to a rectangular one at the same time, these points would fall in the exact same place. That's what that means when you convert. So our next example is -4 pi over 4. So this time r is -4 and theta is pi over 4. So x is going to be -4 times cosine of pi over 4, which becomes -4 times radical 2 over 2. And again, I'm going to do the division first. So we end up with -2 radical 2. Y is going to equal -4 sine of pi over 4, which becomes -4 times radical 2 over 2. And we get that y equals -2 radical 2. And it does make sense that x and y are the same because when I evaluate sine and cosine at pi over 4, they are the same as well. So we end up with -2 radical 2, comma -2 radical 2. So now we want to take a look at converting from rectangular coordinates to polar coordinates. So if you're giving something an xy, to figure out its point with polar coordinates r theta. So the way we find r is given by the equation r squared equals x squared plus y squared. And this just comes directly from the Pythagorean theorem where the r is the hypotenuse. And the way we find our reference angle is you can actually change this alpha to theta is we do the absolute value of y over x. And x cannot equal 0, and again, theta is a reference angle. So what that means is it's going to give us theta in quadrant 1. But our polar coordinate isn't necessarily always going to be in quadrant 1. So we have to know what to do when that occurs. So to figure out what theta is given your polar coordinate will be in quadrant 1, you just keep it. Theta is going to stay theta. But if your rectangular coordinate is in quadrant 2, that's where your polar coordinate should be as well. So you're going to subtract the reference angle from pi. When we're in quadrant 3, we're going to add our reference angle to pi. And if we are in quadrant 4, we are going to subtract our reference angle from 2 pi. So again, this is a reference angle that based upon what quadrant the polar coordinate is going to lie in, we need to determine how we find that theta. Let's go ahead and take a look at an example. So we want to find the polar coordinate whose rectangular coordinates is radical 3, 1. So we start with finding our radius, the r, the distance. So r squared is going to be the square root of 3 squared plus 1 squared. Radical 3 squared is 3, so we end up with 3 plus 1, which means r squared is 4. Take the square root, and r equals 2. Typically, we always assume r is positive so that when we find our theta, we don't have to apply a negative distance to that. So we're going to always assume that r is positive. And also, we are in quadrant 1, so it should be as well. Now we want to find theta. So we do tangent of theta equals the absolute value of y, which is 1 over radical 3. Now the absolute value of 1 over radical 3 is going to stay 1 over radical 3. So theta is going to be found by doing the tangent inverse of 1 over radical 3. And this is a value on the unit circle, so you can use your unit circle to find theta. So if you use your unit circle to find theta, you get that theta is pi over 6. And because our rectangular coordinate is in quadrant 1, our polar coordinate will be as well, which means we don't have to touch theta, and our polar coordinate will be 2 comma pi over 6. Next, we want to take a look at the point 0, 3. So we start off by finding r squared equals 0 squared plus 3 squared, which is going to become 0 plus 9, which means r squared equals 9. Take the square root and r equals 3. We set up to find theta. We get tangent of theta is the absolute value of 3 over 0. So that would mean theta has to equal the tangent inverse of 3 over 0. But as we saw in our definition, x cannot equal 0 because we cannot divide by 0. So if we think about where this rectangular point would lie, if I draw an x and y axis, the point 0, 3 is going to be on the y-axis, which means my polar point should also appear in the same place when graphed, which means the only way for the point to appear on what would be a y-axis in a polar coordinate would be if theta had an angle of 90 degrees, or pi over 2. So then my polar coordinate is 3, pi over 2. So the last thing we're going to take a look at is converting equations between polar and rectangular coordinate systems. And then we're also going to talk about how to identify the type of graph that would be expressed by each. Now you're not going to have to worry about understanding polar equations as much in section 4 because the main thing to get from this is the conversion and the graphing of polar coordinates. We will talk more about polar equations in section 5, but it's still a good idea to see how the polar equations relate to our rectangular equations as well. So we want to convert x squared equals 8y to a polar equation. So what we're going to do is we're going to use that conversion equation that we used with points, the fact that x equals r cosine theta and y equals r sine theta. And after we replace x and y with those equations, we then solve for r. Polar equations are always of the form r equals. So once we replace x and y, we want to work on getting r by itself. So that means my equation is going to become r cosine theta squared equals 8 times r cosine theta. Squaring r cosine theta gives us r squared cosine squared theta. It's going to be equal to 8r cosine theta. So because we want to solve for r, we have to get every term that contains r on the same side, which means we subtract 8r cosine theta from both sides. So we have r squared cosine squared theta minus 8r sine theta. These should all be r sine thetas. My bad. So r cosine squared theta minus 8r sine theta equals 0. Okay. Now we notice both of our terms that contain r, they only have one in common. So we're going to factor out that r. So we're left with r cosine theta minus 8 sine theta, cosine squared theta, minus 8 sine theta in parentheses equals 0. And because our equation is equal to 0, we can take each equation that contains r, set it equal to 0, and solve. So that leaves us with r equals 0 and r cosine squared theta minus 8 sine theta equals 0. Anytime you're converting to a polar equation you end up with r equals 0, we're going to discard that because that's not really going to be an equation. It's going to be a point, and we want an equation. So we're going to solve r cosine squared theta minus 8 sine theta equals 0 for r. So our first step is going to be to add that 8 sine theta to both sides. So we have r cosine squared theta equals 8 sine theta. And then we're going to divide by cosine squared theta. So our polar equation is going to be r equals 8 sine theta over cosine squared theta. Now we haven't talked about how to identify what graph this would look like in a polar coordinate system. That's where the rectangular equation comes into play. So our original equation of x squared equals 8y. Okay. When graphed, this gives us a parabola, which means our polar equation should also graph to be of the same form, which means we're going to end up with a parabola when graphed in a polar coordinate system. And Desmos does have a polar coordinate system. If you hit that little wrench in the top right corner of Desmos, at the very top it has two graphs, and the right one is the polar system. And you can switch to polar form and graph this equation and see a quadratic in a polar system. So when we're converting a polar equation to a rectangular one, so r equals 4 sine theta plus 6 cosine theta, we're actually going to use that r squared equals x squared plus y squared, and we're still going to use the x equals r cosine theta and the y equals r sine theta. Because if I were to solve for sine and cosine using these equations, we would actually get that cosine theta equals x over r and sine of theta equals y over r. And that's what we're going to use here to help us convert. So I'm going to go over here, I'm going to write r equals 4, and then I'm going to replace that sine of theta with y over r plus 6, and I'm going to replace the cosine of theta with an x over r. So now we have r equals 4y over r plus 6x over r. And if I notice, I now have two fractions with the same denominator. So we can write this as r equals 4y plus 6x all over r. So when I'm trying to convert to a rectangular equation, I want x's and y's to be by themselves. So I'm going to multiply both sides by r. We're going to get r squared equals 4y plus 6x. Well, if we look over here, r squared is x squared plus y squared. So I can replace this left side with x squared plus y squared equals 4y plus 6x, and then I'm just going to get my equation equal to 0. So we get x squared plus y squared minus 6x minus 4y equals 0. And this would be the equation in our rectangular equation. And if you remember, this is actually the equation of a circle. So if I were to graph either the polar equation in polar coordinates or a rectangular equation in our xy plane, both of them would represent a circle. So we're going to do the same thing with r equals 18 sine theta, but this time I only have to replace the sine of theta with y over r. So we get r equals 18y over r, still multiplying both sides by r. So we get r squared equals 18y. We're going to replace that r squared with an x squared plus y squared. And then our last step is to subtract the 18y. So we end up with x squared plus y squared plus 18y equals 0. And this is still a circle. Last example, we want to convert y equals 5 halves x plus 1 to polar form. Well, as a rectangular equation, this is a line. So when I graph it as a polar equation, it should also be a line. So we're going to use the r sine theta and r cosine theta. So y becomes r sine theta equals 5 halves times r cosine theta, then plus 1. So we end up with r sine theta equals 5 halves r cosine theta plus 1. Because our goal is to solve for r, we want everything within r to be on the same side, which means we're going to subtract that 5 halves r cosine theta. So we get r sine theta minus 5 halves r cosine theta, still equal to 1. So now I can factor out that r, and we have sine of theta minus 5 halves cosine theta equals 1. And to get r by itself, we divide by the sine theta minus 5 halves cosine theta. So our rectangular equation is going to be r equals 1 over sine theta minus 5/2 cosine theta. And again, if you were to go into Desmos and graph this in that polar coordinate system, you would end up with a line. The most beneficial part from this section, again, don't worry so much about the equations, converting the equations, but make sure you know how to plot polar coordinates and you know how to convert between polar coordinates and rectangular coordinates and vice versa. That's the main thing you need to get out of this section. This last thing we did, again, is just kind of an introductory to what we're going to be doing in section 5.